All right, this is to go over the stuff we did in class, 'cause I know a bunch of you missed this. So this quick little unit at the end is to talk about rotational energy and angular momentum. And we're going to start with a kind of a demo we did in class, but if you weren't there, you would have missed it. But I think you probably saw something similar. So here we have a marble that is released at point A. So this is a kind of like a little curvy wood roller coaster track. And it travels down to point B. And we wanted to predict how fast the marble will be traveling at point B. And we knew we measured the change in height from A to B to be 20 centimeters. And we know the marble has a radius of 1.9 centimeters. And we did this using regular conservation of energy, and we got a speed of about 1.96 meters per second, or 2 meters per second if we use 10 newtons per kilogram for our gravity constant. But when we measured this, we realized that the speed was only about 1.65 meters per second using a photo gate. And we realized something must have been done wrong. So the lost energy must have been going somewhere, because we did our calculations. We measured it really well. There wasn't really any friction. It wasn't sliding. It was rolling along. Our measurements are really good, so there shouldn't have been that much error. And we were trying to figure out why was our numbers different than our prediction. And then we mentioned that, well, the idea of kinetic energy is a measure of the energy of motion. And in our case, our ball is moving along the track. And we did a lot of problems where we had like blocks sliding along tracks and things dropping and things moving. But this was the first time we had an object that was also moving a different way, as since this was a ball rolling, it was also spinning with an angular velocity as it went down the track. And we had talked about that in terms of energy, spinning is a type of motion, so we have to also account for the spinning that's going on, because it takes some energy to spin that thing. So what we're missing here was the spin energy that this ball was accumulating as it was rolling down the track. And then we developed an equation that was similar to our linear kinetic energy equation. So we had our linear kinetic energy as 1/2 mv squared, and we had this idea of a new rotational kinetic energy, which was 1/2 the moment of inertia times omega squared. And then we did a quick check to see if our units work out. So our units of kinetic energy were in kilogram meters per second squared. And if we check our units of rotational energy, since they're both forms of energy, they should have similar units. We get units of moment of inertia are kilogram meters squared, and then our units of omega are just per second squared, since it's squared. And we get the same units. We get kilogram meters squared per second squared for both, as they're both types of energy, and the units work out. So we have this new idea of another form of kinetic energy, a rotational kinetic energy. And we can go back to our situation and analyze it. And then one last thing we remembered, or we wanted to make sure we take into account, is that, remember, as long as something is not slipping, if our ball is rolling, we can convert omega into velocities using omega equals v over r. So let's go back and analyze our situation using this new idea of rotational kinetic energy. The one thing we do need to do though is, if we go back and look at it, we do need to know the moment of inertia of our object. So we have a sphere. So the moment of inertia of a sphere is going to be 2/5 mr squared. So we're going to use that in our problem. So we can start with our regular conservation of energy, but now we're just going to include rotational energy. So at point A, our ball is released from rest, so we just have potential energy due to gravity at point A. And at point B, we have, I'm going to assume if we set our zero height to be at point B, there is no potential energy due to gravity at point B in our case. So we have just kinetic energy at point B plus the rotational kinetic energy at point B to worry about. And again, we're going to make sure we don't forget that we can use omega equals v over r to convert things. Now we're trying to figure out how fast this thing is going. So we want to solve for velocity. And also, let's not forget that the moment of inertia of our object is, since it's a sphere, is 2/5 mr squared. So again, just like our other problems, we have our conservation equation we wrote down. Now we're going to go on and expand those numbers. So for potential energy due to gravity, we have that's equal to mg times h. I'm going to use big H for now, where big H is the 20 centimeters or 0.2 meters that they gave us. Our equation for linear kinetic energy is just 1/2 mv squared, and our equation for rotational kinetic energy is going to be 1/2 I omega squared. And these are both at point B. Actually, what we need to be, because there's no velocities at point A, but it's fine to write them at point B. Now again, so we have our energy conservation set up. We have an equation for it. Now again, we can do our next thing where we expand that even further. So first, let's sub in our idea of kinetic, or our idea of moment of inertia. And also, because they're trying to solve for velocity, and now we got to make sure we're a little bit careful here, since our sphere is rotating around its outside. The radius of rotation is the whole radius of the sphere. So the radius in our moment of inertia and the radius of our rotation is the same. So we don't need a second variable. This was something like a I don't know, a yo-yo or something where it was rotating at a different radius than the actual radius of the object. Then we have to use different ones. But in this case, they're the same. So I'm also going to substitute this in for omega and substitute moment of inertia in to be able to solve this. So we're going to get mgh stays over here, and that's going to equal, got 1/2 m. I'm just going to get rid of the subscripts for now just to make life a little bit easier. V squared plus 1/2. Now the moment of inertia ends up being 2/5 mr squared. And omega, we're subbing in v over r, so we get v over r, the whole thing squared. Now at this point, you're going to notice something really nice is going to happen. All the terms have a mass, so the mass is going to cancel out. This r squared here is going to be canceled out by the r down here, since the r down here is also squared, so those are going to cancel out of each other. And we realize that this just turns into gh on the left equals 1/2 v squared plus, let's see, 1/2, so this 2 is also going to cancel out that 2, so plus 1/5. And all that's left in this whole term here is just another v squared. Or we can say a half is really 5 tenths, a fifth is 2 tenths. So this, we can combine these two and get exactly 7 tenths v squared. And now to solve for v, bring the 7 tenths to the other side. So that's 10/7 gh. That is equal to v squared. So we end up with that our velocity at the bottom is going to be equal to the square root of 10/7 gh. Let's do a quick check of units to make sure we didn't make some mistakes. Let's see. This is unitless. This has units of meters per second squared. This has units of meters, so that gives us meters squared per second squared, square rooted, which is meters per second, which is the units of velocity that we're looking for. So in this case, we have an equation that solves for velocity, and the nice thing is the mass disappears. And we can put numbers in this. So we get 10/7 times 9.8 times g, or times h, the square root of that, and this ends up being about 1.67 meters per second, which is much, much closer to our observed value of 1.65 meters per second. So that's one type of problem where you have an object that's actually falling and also rolling as it's falling. We can solve it using regular conservation energy. We used to have to add this new kinetic energy term. So let's look at one more. So here we did this problem in class using torques and forces. It was a little bit annoying to solve. Here we have a mass attached to a pulley. The mass is falling, and we want to figure out how fast is the mass going to be going when it falls some distance delta h. Now I'm going to make one little assumption to make our life a little bit easier. I'm going to assume that this small pulley here is very small compared to the big pulley, just to make us calculating the moment of inertia a little bit easier. And again, when we drop this in class, we observe that the speed of this thing falling is not as fast as if we just drop something. So somehow when we drop this, all the energy, the potential energy stored in this mass before it falls, has to go somewhere else. It's not just going into the speed of the mass falling. In this case, it's going into the rotational speed of the pulley as well, because the pulley, even though the pulley itself isn't falling, the pulley starts to spin, because in this case, we can't assume our pulley is massless anymore. So again, we're going to start with our generic conservation energy equation. So at the top, we have nothing is moving, so we just have some potential energy. Let's call it at 0.1. That's before the mass is dropped. And that is going to turn into kinetic energy of the mass plus rotational kinetic energy of the pulley as it goes down. Now again, we have to use a couple terms. We want to make sure we use, for the pulley, we're going to say the moment of inertia of the pulley. Let's assume it's a cylinder. It's just going to be 1/2 m. Now let's see, this is going to be the mass of the pulley squared, which is 2 in our situation. Actually, I guess it would be mass, I guess I called it a disk, so mass d. And again, don't forget that we can convert the angular velocity of the pulley to the linear velocity of the, in this case, of the string. So we got to be a little bit careful here. Since the string is attached to the small radius here, we don't want to use the full radius of the pulley to convert our angular motion to our linear motion. We want to use the mass of the part that it's hooked up to. So we can say that the angular velocity of the pulley is equal to the linear velocity of the string divided by radius 1. And now again, we can expand our equations. So we get for our potential energy, since I called the height delta H, we're just going to call it, this is just going to be mg delta H. Now we got to be careful. The thing falling is mass 1, so make sure we don't forget that subscript. And that is going to equal to 1/2 mass 1 v squared. So this is the kinetic energy of the falling mass plus 1/2 I of the disk times omega squared. Now, again, we can expand this again. The left side is okay. The kinetic energy is okay. We're going to, so this is just going to stay m1 g delta H equals 1/2 mv squared, or m1 v squared, plus now our moment of inertia is 1/2 mass of the disk, r of the disk, which we call 2 squared, and omega we're going to sub in again v over r, but v over r1, the whole thing squared. So this time we cannot cancel out our radiuses because they are different radiuses. But we know all these values. They're given us, they're things that we can measure. So we can just put numbers in and solve this. I guess we can clean up a little bit. I guess you can turn the 1/2 times 1/2 into a 1/4 if you want to. But at this point, you're just going to put numbers into this and then solve it. I'll leave this for you to do. So at the end, if you solve it algebraically, you get v squared equals, now this is going to be a lot more messy than the last one because we can't drop things out, m1 g delta H divided by 1/2 m1 plus 1/4 mass of the pulley times r2 squared over r1 squared. And that's all on the bottom of the fraction. And when you put this in, you get v squared equals about 0.24 meters per second squared. And that means that the velocity when it gets to the ground is equal to 1/2 meters per second. And again, if we want to now find the angular velocity, we can just go back and plug that into there, and you would get an angular velocity of about 10 radians per second. And again, this velocity of 1/2 meter per second is slower than if you just drop this thing, that delta H of 1/2 meter. So again, it's the second type of problem, similar to the last one. Look at the objects that are moving. In this case, the pulley is spinning, so the pulley has rotational energy. The pulley is not dropping, though, so it doesn't have any linear kinetic energy because its center of mass isn't moving anywhere. The only tricky part here was we had to be really careful with these radiuses because they were different this time, so they won't cancel out. Let's try one more situation. So in this case, we have a ball rolling down a hill, and then it goes through a loop-de-loop. In this case, they want us to figure out how high we have to release this from so that when it goes around a loop-de-loop, it actually makes it through. Now, in this case, there's a couple things to know. So it's a sphere again, so we can use moment of inertia of 2/5 mr squared. And we solved a similar problem to this back when we did centripetal acceleration, and we realized that when the ball gets to the top, it has to be going a certain speed. It has to be going a velocity where the centripetal acceleration ends up having cancels out gravity so that it doesn't fall off. So it has to be going, if it just can't be going 0. Now, if this is like going over a hill, we could release it from the same height as the hill. It would just make it over the hill. But since if we want it to stay inside the circle, not just fall straight down, it needs to be moving at the top. And we had solved this already, so let's just do a quick little review. So back in that unit, we solved that the velocity of the ball to get around the curve to stay in contact with the track, it must be going the square root of g times r to stay around that track. So because this was a centripetal acceleration problem, we know the velocity at point B must be equal to that. So again, we can use that to solve this. Again, we'll start again. We're releasing something from rest. The beginning is nice and easy. So we have the potential energy, let's call this point 1 over here. And we got point B, potential energy at point 1. It's not given a push, that's all we got. Must equal the kinetic energy at point B plus the rotational kinetic energy at point B. Plus, now it's not at 0 height over here at point B. It's at some height over here. So we're going to also have to add the potential energy at point B as well. There's our conservation of energy. Again, we can use the fact that omega equals V over R. And in this case, since omega equals V over R, omega is going to be equal to square root of GR over R. Now I'll expand our conservation equation. We have, let's see, mg big H in the beginning, and that equals 1/2 mv squared plus 1/2 times I times omega squared plus mg. Now the H at point B, since this is the top of a circle, and circle has a radius of r, the height is then 1r plus another r, so the height at point B is actually 2r. I'll expand it a little bit farther. We got mgh equals 1/2 mv squared plus 1/2. Our moment of inertia, since it's a sphere, is going to be 2/5 mr squared. Omega, we said, was gr over r. That's squared, so this is omega squared is going to be gr over r squared plus mg times 2r. And now something nice is going to happen. If you look at this, all of our terms have a mass. The mass is going to go away. All of our terms, actually, I can sub one more thing in. Let's erase this and just stick it in there. This v is also going to be, so v squared is going to be square root of g times r. So v squared is just gr. So now all of our terms also have a g. The g is going to go away. And if we look, so does anything else cancel out? I do not think so. So we get on the left side, we actually are solved for h. Everything dropped out on the left side. So we have the height we need to drop from, which is what we're looking for, equals, let's see, we got 1/2 r. We have plus 1/2 times 2/5. And now if we look at this r squared and this r squared also cancels out. All that's left is this little r up there. So we got plus 1/2 times 2/5. The 2's drop out. So we got a 5th r. And then over here we have another 2r. And if we add those up, we get 2r plus a 1/2 plus a 5th. That gives us, I guess, 2 7/10. I guess I can write it as a mixed fraction times r, which is also known as 2.7r. So that means the height we'd have to drop this from is, now, if this was a block sliding like on ice, and it was trying to go over a hill that's 2r tall, you could drop it from 2r, it would go up to 2r. If it's a block sliding on the inside of a circle, I believe in that case it would be 2.5r you'd have to drop it from. But now since we have a sphere that's rolling, we need a little more energy to go into the rolling part. We need a little more potential energy in the beginning, so we need to drop it from a height of 2.7r. And what's also nice to notice here is that a lot of things kind of dropped out here. The mass, it doesn't matter the mass of your object. All the mass will kind of travel and go through there. Doesn't matter what the mass is. And what also seemed to not matter is the actual size of the ball you're rolling down, because actually I dropped things out. This should really be the r of the ball. Otherwise I forgot the subscript, but it cancels out anyways. So that doesn't matter inside there either. All that really matters is how high you dropped it from. And hidden inside here is the shape of the object. So that 1/5 right there, that kind of that's a leftover part of our shape factor of our object. So that matters as well. And that gets into what would you need to drop if it was a hollow sphere instead that had a moment of inertia of 2/3 mr squared. Well, in that case, we'd actually need to drop it from a little bit of a higher position. Since there's a greater moment of inertia, it still needs to go the same speed when it gets to the top of B, but more energy is going to be put into its rotational energy, so it needs a little more energy in the beginning. So you need to, I is greater, so you need a little more height to get a little more potential energy, to get a little more kinetic energy when it gets to point B, to account for that extra rotational energy that you need. So that is the end of the quick little rotational energy part that you guys missed in class.